All right, so we're going to talk about the three states of matter, the solids, liquids, and gases, and we're going to start off with solids. Solids have a definite shape and a definite volume, as you should know, but are these particles in motion? Your first thought might be, no, they're not in motion, but in actuality they are. All the bonds and all the atoms actually have constant vibrations going on within the solid. We might not be able to see them or detect them, but they actually are happening at the atomic level. The only time those vibrations actually cease is at zero Kelvin, or absolute zero, or negative 273 degrees Celsius. And in reality, we actually have never even reached that point. So in reality, that's actually like a theory. It's a theoretical point. So yes, all these particles are still in motion. Let's talk about the density. The density of solids, you would think, the density is actually the compaction, or how tightly close these particles are to each other in a given volume. So solids, you would think, have actually, most of them do, have a higher density than their liquid and solid counterparts. Except in water. Water is a rare exception where the density of the solid, or ice, is actually lower than the density of the liquid. That's due to the way it hydrogen bonds and the way it actually forms its solid. It's actually less dense than its liquid, which is the reason why ice floats. Most solids actually don't float in their liquid. Let's talk about the five different types of solids you might come across in chemistry class. The first one being atomic solids. Atomic solids are just atoms that are attached to each other in a solid form. They're pretty soft, they have a low melting point, and they're actually poor conductors, meaning they do not conduct electricity. They don't have those free-floating electrons that are able to conduct electricity. These atoms might be group 8 elements, neon, argon, things like that, that actually form atomic solids. Next would be molecular. These are where molecular compounds come together, and the intermolecular forces are what's keeping them all together. There are molecules that take place in this. And those guys are fairly soft. They too have a low melting point, and they also do have poor conductivity because they don't have those free-floating electrons. And those are typical things like water, sugar, ammonia, things like that. Those molecules that are held together through IMFs or through intermolecular forces, hydrogen bonding, dipole-dipole interaction, or London dispersion. Next would be covalent network solids, and those are just strictly atoms all covalently bound to each other. So not just atoms held together through the lack of energy, it's actually they're all bound to each other. They're all sharing each other's electrons. These guys are really hard molecules because they are all covalently bound. They have a high melting point, but they're still poor conductors because there's no electrons there to give electricity out. And things like this are diamonds. The carbon in diamonds are all covalently bound to each other to give it its shape. And quartz, silicon dioxide, actually is a covalent network solid. Things in group 4, typically group 4 like carbon and silicon, all have covalent network solids. The fourth one is ionic compounds. Ionic compounds, or ionic solids, are all made up of their ions, cations and anions, all bound together through electrostatic forces. These guys are hard. They're brittle. They have a very high melting point. It's really hard to separate those ions from each other. And they too are poor conductors when they're in their solid state. If you put their solid state in water, making a solution, that actually makes the conductivity extremely high because those guys separate from each other. And we have those access to those electrons. But in just the solid itself, they're actually very, very poor conductors. Any type of ionic compound is what I'm talking about. Table salt, calcium carbonate, things like that. Anything that's ionically bound to each other. Lastly, we have metallic bonds. And metallic bonds are made up of all metals. And the reason I have C of electrons here is because how metallic bonds actually are created are they're held together through their positive cations, and then their valence shell electrons are kind of make the C of electrons, or delocalized electrons, shared all throughout the whole solid. So that's where the C of electrons comes from. Because they have this flow of electrons within the solid, they're extremely good conductivity. They're good conductors of electricity, which is the reason why, coming from those free-flowing electrons within the metal. And any and all metals actually make metallic bonds or metallic solids. Next type of phase is liquids. Liquids have no definite shape, and they do have a definite volume. They have characteristics, one of them being fluidity. Fluidity means the ability to flow. So things that they have over solids, they actually can flow over themselves, along with gases. Gases can do this too. Gases can actually do it a little bit better than than liquids can. But the opposite of fluidity is viscosity. It's how much resistance to flow it is, how slimy it is, how much it doesn't like to flow. So the bigger the size, the larger the viscosity, or the more likely it won't flow. So let's take these hydrocarbons, for example. This large hydrocarbon is not going to flow as much. The intermolecular forces, the London dispersion forces that hold these guys together, are actually a little bit stronger here because there's more electrons than in its smaller hydrocarbon over here. This guy actually has a lower viscosity, meaning it flows greater than this guy, which has a higher viscosity. As you increase temperature, the viscosity also decreases. So if you increase temperature, its fluidity does increase. It's able to flow more. It's able to break those IMFs, or those intermolecular forces, and able to flow more, making its viscosity lower. So these are indirectly related, and these guys are size and viscosity are directly related. One of the last things we're going to talk about in liquids is surface tension. And surface tension is the measurement of the inward pull of a liquid upon itself. So I have a little small illustration down here for you to illustrate this. These guys are all water molecules. We have the negatively charged oxygen, the positively charged hydrogens. And those dotted lines are the hydrogen bonds that attach not attach them, but bring them together. And so on top of here is the surface of the water. So here's the water down here, and here's like air. If you go on like a creek walk, and if you go on like a hike in the woods, you might come across a creek, and you might see bugs kind of walking on water. How do they go about doing that? Well, here's an example of a bug's leg. And notice the bug barely touches the water. It has a very, very small place where it touches the water on its leg. And because it has a small place, this hydrogen bond actually keeps the water together, and is able to make the bug walk on top of it. That's because the surface tension, or this bond, is actually not bond, but its attraction is actually pretty strong compared to this light weight of this bug. So it's able to hold it up. So this surface tension is different for each kind of liquid. Water has a pretty good surface tension, so it's able to hold the bug's leg on top of it. And lastly are gases. Gases have no shape and no volume, and there's actually a whole ton of laws and a whole ton of rules of dealing with gases and their behavior, and we're going to go into that in the next couple of videos. So this actually, in a nutshell, talks about the three phases of matter: solids, liquids, and gases, and hopefully this makes sense.